Hey everybody, this is Mr. Ainsworth, and we're going to get into a little prep here for Activity 1C1. And to do that, though, we're going to investigate a couple new concepts here dealing with our main theme so far, which is called closure. Okay, so let's get a little bit deeper here and let's explore a couple concepts. First of all, I want to talk about what difficulties do you think we might encounter when investigating closure on infinite sets versus finite sets. Now you got to understand the difference of the two, okay? Big difference between an infinite set, okay, versus a finite set. Okay, so let's just stop right there and let's analyze that. Okay, now an infinite set is like the set of natural numbers. All right, so let's take the natural numbers. All right, now if you're not sure what those are, okay, you got to go back to grade school, okay? You first started counting not at 0 but at 1, okay? In fact, back thousands of years, they had no idea what 0 was. There was no concept of 0 in the beginning. People start counting with 1. All right, so we got 1 here, all right, 2, 3, 4, 5, etc., okay? All the way out to infinity. All right, this is the infinite symbol. Okay, so we got a symbol here. It's like a sideways 8 actually. It stands for infinity. Okay, to infinity and beyond, as Buzz Lightyear used to say. All right, and the natural numbers is an infinite set. They never stop. Okay, whatever natural number you can come up with, that I can always add 1, and it goes further out there to infinity. Okay, so that's an example of an infinite set. A finite set, you saw that last time. So if you take a set of, let's say, 3 numbers, negative 1, 0, and 1, or any set you want comprising of 3 numbers or 2 numbers or even 100 numbers or even 1,000 numbers, okay, that's still finite. So if it's not infinite, it's called finite, okay? And so, just look at the word infinite. It starts with that prefix in, and as you guys know from English, okay, that means not. Right? And if it's not finite, meaning a specific number of sets, that means it goes on forever and ever and ever and ever. Okay, so what difficulties, let's go back to the main question here, do you think we might encounter when investigating closure on infinite sets? Again, we're talking about closure here. All right, now the first thing that we did back when we first started discussing this is if I asked if a set was closed under any operation, whether it's multiplication, addition, subtraction, squaring, it doesn't matter what it is. All right, the first thing I said we need to do is you list out all possibilities. The question is can you list all possibilities of an infinite set? So my first question to you right now is can you list, okay, all the possibilities, okay, for an infinite set. Infinite set. Can you do it? For example, if I ask you if the naturals are closed under addition, okay, so if I ask you this, are the naturals closed under addition? Let's say I asked you that. Okay, now the naturals, as I said, are the numbers from 1 to infinity, right? And so try listing them. Try listing all the possibilities. Okay, because that's what we did earlier in our previous activity, right? Try listing all the possibilities. So let's do it. Okay, so 1 plus 1 is 2. 1 plus 5 is 6. 1 plus 8 is 9. Okay, 2 plus 100 is 102. 5 plus 1,000 or 10,001 gives you gives you 10,006, right? So 10,006. I mean, if you add up any two of these natural numbers, is it still natural? That's what the question is. I said, are the naturals closed under addition? So if to do that, you would have, or to prove that right now without any techniques, more advanced techniques, you would have to list all possibilities. But can you do that? Can you list all possible sums of two numbers and show that the sum of any two naturals is a natural? In other words, that you have to show that a natural, all right, plus a natural equals a natural. Okay, can you show that? And the answer is obviously no, because there's an infinite number of numbers, so there's an infinite number of possibilities. So my initial question was, can you list, okay, the key word is list. Can you list all the possibilities for an infinite set? And the answer is no. Okay, not on this one. Okay, you can't list it. So how in the world do you prove such a thing? How do you prove that a natural plus a natural is a natural? I mean, it is, but how do you prove that? And that's, for a discussion later on. So the question is what difficulties do you think we might encounter when investigating closure on infinite sets versus finite sets? Well, you just can't list them all, people. Okay, you can't do it. So how in the world do you do that? How do you show that an infinite set is closed under an operation when you can't list them all? Okay, it's not possible to list an infinite number of possibilities. You just can't do it. Just not going to happen. It ain't going to happen. Okay, so how in the world do you do it? So we'll talk more about that later. Okay, but what we want to do is this. When we investigate closure, so let's go back to the main question. So when investigating closure, let's make sure we do a few things, okay? So the keyword is closure. So when investigating closure, the first thing you do is you try to explore all the possibilities. And you're going to see me and hear me say this all the time, okay? Explore the possibilities, okay? So explore the possibilities. I'm going to say that to you all the time. Okay, so when you don't know about something and you're trying to figure out if a set is closed or not under any operation, and there are many, by the way, they're not just four, adding, subtracting, multiplying, dividing. There's squaring, square rooting. There's cubing, okay? There's logging. I mean, there's all kinds of things. I mean, there are so many different operations that you can use. All right, so just don't get stuck with the basic four operations, people, because there's a lot more than that. All right, but you want to explore the possibilities, and what that means, people, is that you want to list, okay, list them out. Okay, I'm going to put an exclamation point there, list them out. Okay, that's the first thing you do, if you can do it, if it's a finite set, and there's only a few possibilities in the list. You saw that in my previous activities and discussions here where I had like only maybe 9 possibilities, and I was able to list them and show something's closed. So if it's possible, do it. Okay, so the first thing you try to do is list them. If you can't, well, then you try something else. Okay, we also saw that it's also possible to show all possible outcomes, outcomes through a diagram. Okay, so through a diagram. So I'm going to bold this because this right here, all right, it sounds simple, but it's very, very powerful. All right, so you can actually show all the possible outcomes, not by listing, but in a simple diagram. And I showed that to you guys before too. So I'm just going to refresh your memory. So if you have -1, 0, and 1, and 1 right there, and let's say that's your set. And let's say you want to show it closed under multiplication. Okay, so show closed under multiplication. Okay, all you had to do is draw this simple little diagram here. So I'm going to do that again. So I'm going to put a time sign here, put the elements here, put the elements up top. All right, and fill in the possibilities. All right, -1 times -1 is 1. -1 times 0, yeah, well, that's 0. -1 times 1 is -1. And then second row, multiply everything by 0. So 0, 0, 0, because anything times 0 is 0. Third row, multiply all these numbers by 1. So 1 times -1 is -1. 1 times 0 is 0. 1 times 1 is 1. Okay, and these are all the outcomes. And in this case, there are 9 of them. So instead of listing, you can do it through a diagram. All right, now, if you cannot list and you can't show it through a diagram, then maybe it is not closed. And to show not closed, you need to provide a counterexample. So, to show that a set is not closed, let me actually write that. To show that a set is not closed, comma, okay, to show that a set is not closed, in fact, let me bold that. Not closed, okay, show or provide a counterexample, okay. Find a counter example. Okay, an example that shows it's false. Okay, and so when that happens, you just provide one. One is sufficient. Okay, one is sufficient. All right. So let's take a look at this here. So in this right here, what we're talking about here in the prep we get for 1C1 is that we're going to jump to the infinite sets. Okay, we're going to go from finite to infinite. And to do that, we're going to have to get creative here. So if a set is closed on an infinite set, you don't have the skills yet to prove it. We'll prove that later. All right. However, if it's not closed, just find a counterexample. Find an example to show that it's not true, and it's only needed to show one. Now, before we get there, we're gonna be dealing with a new set of numbers. Instead of the naturals, we're gonna jump into the integers. But if you don't know what the integers are, which is usually the case a lot of times, because we don't do enough number theory here in modern mathematics. Okay, let's go back through it and let's go back to the beginning. So let's talk number system here. Okay, so we're going to start off with the naturals, okay? So the naturals. Now, every set has a symbol, and the symbol for the naturals is it kind of looks like a capital N, all right, but it has 2 vertical lines. So I'm going to put the symbol in here. Okay, so it's the capital N with 2 vertical lines. Let me draw it real big here. Okay, and by the way, you can get all these symbols online. If you just Google number set symbols, all of these symbols will come up here. So we're going to use the capital N with the 2 vertical lines here to represent the set of naturals. Okay, and what does that look like? Well, let me put them up here. So there we go. All right, 1, 2, 3, 4, 5, and 6, and all the way to infinity, right? It's an infinite set. And that is the set of natural numbers there. Okay, so it's natural to start at 1. Just that's how I remembered it as a kid, and it's an easy way to do it. Now over here on the left, we're going to write down under what operations is it closed. Okay, now so it's closed under what operations? Well, if you add a natural to a natural, you're going to get a natural. Okay, we talked about that. 1 plus 5 is 6. Okay, that's natural. 2 plus 10 is 12, and that's natural. So it's closed under addition. It's also closed under multiplication. 2 times 4 is 8, that's natural. 5 times 4 is 20, that's natural. So it's closed under multiplication. It's not closed under division, okay? Because 1 divided by 2 is 1/2, and that is not a member of the set. So go ahead and slash that. So it's not, I'm not going to put division here. It is not closed under division. No. And it's not even closed under subtraction. Okay, so I'm not going to put the subtraction symbol there because 1 minus 2 is -1, and that's not a natural number. All right, so I'm going to slash that too. All right, it's not a member of the natural numbers here because it's negative and not positive. Okay, so remember that, man. All right, natural numbers are all positive whole numbers. Okay, they're all positive whole numbers, and they're not fractions either, so keep that in mind. Now, the number system here had to get bigger over time because, believe it or not, 1 minus 1 is 0, and 0 is not a natural number. So let's throw 0 in the mix. All right, and let's talk about the set of natural numbers, including 0. So we're going to put the naturals here. All right, and 0. Okay, so we're going to use this symbol here. We're going to use the capital N and little subscript 0. Now, in grade school, that was called the set of whole numbers. Whole numbers, okay? So whole numbers start at 0, not 1. So 0, 1, 2, 3, 4, etc., all the way to infinity. So we say it's the natural numbers with 0 involved or included. The question is what are they closed under? So this set here, when you throw 0 in the mix, what are they? What operations is this set closed under? So it's closed under, well, if you take a whole number or a natural number, we'll call them whole numbers, even is 0, and you take 0 and add it to any other number, you get that number. It's like 0 plus 4 is 4, right? 0 plus 4 is 4. All right, 1 plus 0 is 1. And then 2 plus 5 is 6. Well, guess what? Those are all natural numbers. It's in the set. So it's closed under addition. It's closed under the multiplication. Same thing applies. If I change the multiplication, 0 times anything is 0. That's still in the set. 1 times anything is the number. That's in the set, and so on. But it's not closed under division, and it's not closed under subtraction for the same reasons as above. Okay. Now, later on, when people and civilizations got more sophisticated, they started figuring out that you need negative numbers too, because sometimes you get negative numbers. Like if you have $2 in your pocket, but you owe your buddy 5, you're still going to owe 3, and that's a negative situation, right? So we had to invent the negative numbers. And so if you take all the negative whole numbers, like the opposite of 1, which is -1, the opposite of 2, which is -2, and the opposite of 3, which is -3, and you throw the negative whole numbers in the mix, you get what's called the set of integers. Okay, so let's integers. All right, now these numbers here are the negatives. All right, so -2, -1, 0, it's a positive, and it keeps going in both directions, so in the positive sense and in the negative sense. And since the guy that invented the negative numbers here was German, all right, so the Germans figured this out first before anybody else. All right, they came up with the Z, okay, and it's a capital Z. It looks like this, with another slash on the diagonal here. So when you do that, so it's the Z with another slash right here, and that is short for Zahlen. And the reason why they use Z because it comes from the French or the German language, excuse me. So Z for Zahlen. I think it's Zahlen. All right, it stands for Zahlen in German. Okay, and the question is what are they closed under? Okay, and we're going to go as far as this, and then we'll finish the mapping diagram later. All right, because we're not going to go beyond the integers yet. Okay, so what are they closed under? Well, let's see. If you take these two integers here and you multiply them together, or excuse me, you add them together, all right, like 1 plus -2, you get -1. Like -1 plus 2, that's 1. -2 plus 1, that's -1. These are all integers. And it turns out that an integer plus an integer is still an integer. So it's closing under addition. Same thing is true for multiplication. If you take -2 times 2, you get -4, that's an integer. If you take a -2 times -4, you get 8, that's integer. Okay, so it's closed under multiplication. Now this one here is also closed under subtraction, because if you take 1 minus 4, you get -3, and that's an integer. All right, so it's closed under subtraction, but not division, because 1 divided by 4, all right, is not an element of the integer set. All right, so no fractions, so not division. Okay, so having said that right here, let's talk about this set, this very special set of integers. I'm going to even highlight it here. So we're going to focus on integers in activity 1C1. All right, so in fact, let's define that above. So let's put that up here, integers here. And again, the symbol is Z with a little slash. All right, and the integers look like this. It equals to the set consisting of all the negative numbers, 0, and all the positive numbers. Okay, so that's your set of integers. Again, it's the whole numbers here, okay, and the opposites. Okay, so that's those two sets combined form the set of integers. So what in activity 1C1, we want to investigate, what happens, or is the set closed under these operations? Is it closed under addition? Is it closed under multiplication? Is it closed under subtraction? Okay, and so on. Now, to do this, if it's not closed, okay, guess what you have to provide? That's right. If it's not closed, you must provide a counterexample. All right, so let's notate that, okay? Okay, so if, all right, not closed, okay, you must provide a counterexample. You must provide a counter example. So keep that in mind. Really important point there, so make sure you write that down. So if it's closed, you're just going to say closed. All right, if it's not closed, you better give a counterexample and show why. Now after this, then we got bigger fish to fry, and the concepts keep on building up over time. All right, but we're building up understanding of what it means to be closed. And we started off with finite sets, and now we're moving with infinite sets, and we're going to build and build and build and build until we get to the complex numbers in section 5. Okay, that's at the end of the semester. So there you go. Yeah, let's get in groups. Let's work on this, and I will see you in my next prep lesson. This is Aynesworth here. Again, we are in MRWC here in Great Oak High School in the Temecula Valley School District here. And I'll see you in my next lesson. Take care. Bye-bye.